to the February meeting.
Meeting of what? AA?
To start the report.
Oh.
Oh, I thought you were reading.
No.
Welcome to the February meeting of the BBAA. And first off, we're going to start off with the VP report from George.
Okay, I have passed out schedules. I'm going to do it a little differently. Instead of going down the calendar, I put them in groups. And that first group I've got on the board here, I'll come back to that one. The second group is our recurring outreach events that we do every month. Saturday, Sunday, we do Elizabeth River Park, looking at the sun. It's the 8th, this coming Saturday, from 11 to 1. 11 to 1? 10 to 1.
10 to 1.
10 to 1.
10 to 1.
10 to 1. 10 to 1. And then a week or a month after that, the 7th of March, from 10 to 1, Elizabeth River Park. Our Sky Watch will be the following Saturday, the 15th of February.
Which is turned into the rain magnet for Southeast.
Yeah, we hope the weather holds up, clears up. And then Saturday, the 14th of March, will be the next Sky Watch next month. We'll have Garden Stars at the end of March, the 31st of March. The next group is our members only observing events. They're optional. You want to go to them without having to share your scope with the public. We have 4 corn watches every month, before and after Sky Watch, and
New moon.
and night watch. They're near the new moon weekend. So February's corn watch events are the 14th and the 21st, Friday nights, and they sandwich. Well, let's go to the next one. In March, it's the 20th and 27th of March, and those are at Cornland Park, of course. It's a little bit darker there than it is here in the city. Saturday the 22nd of Feb is Night Watch, where you get to go to Chip Oaks Plantation State Park. And a month after that, on the 21st of March, is the next Night Watch at Chip Oaks. And for anybody who wants to go for a week-long star party, and some of you have been there, the Stanton River Star Party is from Monday through Sunday, the 23rd through the 29th of March. And I don't have an address on there. Just go online to their website and get the information, the details, and registration. Of course, tonight is our February meeting, and our next March meeting will be the first Thursday in March, the 5th of March. Now, I'll go back to that group on the top. Those requested outreach events, those are events that we get requests for from schools and scout groups and public activities, and they want us to come and show the sky. And we need volunteers. Usually it's Sean and me and Chuck, sometimes Arch, sometimes Jeff, sometimes Tom, sometimes Jeff Thornton, sometimes a couple other people.
That guy's there sometimes. Mike, right in front.
Mike Webster. Oh, I didn't even see you.
Oh.
Nice to meet you. I'm George Reynolds.
Yeah, nice to meet you, George.
Known you for 30 years.
This is my first time this year.
Yeah, first meeting you've been to for a while.
Yeah.
So anyhow, we need volunteers, and it's easy to volunteer. You go to our calendar, click on the event, and go down to where it says RSVP, and sometimes you'll get a message. I sometimes send out messages, or sometimes the message goes out automatically when it's scheduled. And you have a chance to RSVP and say, yes, I'm coming, or maybe I'll come, and gives us an idea at least how many people might support the event. This coming Saturday, we've got, they call it the Boy Scout Freeze-a-Ree. I don't know how cold it's going to be. I hope it's dry. That's all I care about. We're going to be working toward some parts of the Boy Scout Merit Badge. And that's in Barco, North Carolina. Again, if you don't know how to get to a certain place, go to our events calendar, click on the event, scroll down where it says Get Directions, put in your home address or your starting point address, click on it, and it will give a MapQuest type step-by-step directions how to get there. It shows you on a map. So That's how I got to Sleepy Hole State Park when I was supposed to go to Lone Star Lakes Park.
But you know, it said Sleepy Hole.
I know, I put it on there, because that's what I thought it was. I think,
But we now have.
maybe that's what they, oh, that's right, they submitted that, and then they changed it, but they didn't change it, they didn't tell me to change it on the web. Oh well.
I now have Nikisha's phone number.
Anyhow, so that's this coming Saturday.
Usually that does not happen, usually the
Right.
house is right.
We've never had a problem like that before. This Saturday is the 8th of February. Then on the 24th, it's a Monday night, we go to Carrollton, the Carrollton Library, 2 or 3 times a year. And so it's usually a really fun event. And
It's pretty dark there too.
it's pretty dark. We can
It's
sometimes
surprising.
set up in the parking lot, and sometimes we go in the back where it's even darker, and back behind the building. And if the rain and clouds cooperate, you can see a lot of stars.
Start time? Start time?
Dark.
Dark?
Sunset.
Hang on a second, I've got my list here. Oh, it's right here. Okay. Start time for the Winter Sky Night is 7 p.m. 7 to 8 p.m. Just an hour, but I usually try to get there about a half an hour early to set up. And the same way with the Boy Scouts freezery, that's from 8 to 11 p.m. And I'll try to get there maybe an hour, half an hour early. Okay, on the 3rd of March, Tuesday, Deep Creek Central Elementary School on Shipyard Road has their annual science night. And we
Hey, George,
support
I
it.
have a question.
Pardon me?
I have a question.
What's your question?
How's the 3rd, March 3rd and March 1st, both on Tuesday?
It's a leap year. Kidding.
I'm getting to that yet.
Kidding.
Please wait. Please bear with me. I haven't got to that one yet. Okay, March 3rd is a Tuesday. It's Deep Creek Central Elementary School on Shipyard Road. Now, the next entry on your sheet is incorrect. It says here, no, error on sheet. It says 3-1. It should say 3-10. 3-10. It's a Tuesday. It's at Creed's Elementary School, 920 Princess Anne Road in Virginia Beach.
It must be a week later.
And each, this Deep Creek Central, Creed's Elementary, and Nansen and Suffolk, each of them expect a couple hundred people because it's their big science night.
Yeah,
we had-
all the science nights, we could use help, right?
Yeah.
The Deep Creek one, there's
I've
gonna
asked
be
for-
200-300 kids there.
I've asked for 5 volunteers for each of those events. Okay, and then Wednesday the 18th, another week and the day later, Nansen and Suffolk Academy Lower School at 3373 Pruden Boulevard in Suffolk. It's easy to find, it's right off the main road. They're having their science night. We've been there before too.
We've even had people show up that weren't club members with the telescope and just help. And
That's
just
So,
want them just to show up and help.
Wow.
And then the last
And there's
one,
enough kids to go around, trust me.
the last one that we could use volunteers for is at the end of March, near the end of March, the 28th of March. It's Earth Hour at First Landing State Park in Virginia Beach. We've done this for several years in a row. It's a lot of fun too. We set up in the parking lot and they block it off for us. And there's 2 parking lots, a front parking lot and the back parking lot. They're separated by just a tree line. And we set up in the back parking lot, have the whole parking lot to ourselves, and people come through and look through our telescopes. We point out the constellations and the moon and stuff. The moon will be visible on that night, I believe. But some of these, the moon will not be visible. So Venus will be, and if there's no clouds, maybe we'll see some stars. Hope. But anyway, we could use volunteers. So go to the website, RSVP, go to our calendar, click on the event, and RSVP and volunteer to come. That's the schedule for the next 2 months. Any questions? Besides Chuck's inane question.
his head was in the
Okay, the next thing I've got, almost forgot. I've got some awards. We,
Where's Bruce?
as you, most of you know, what is this?
You take it, you can award it to him.
Oh, sure. Yes, okay.
And where's Bruce?
Okay, yes, that's a special one. But we are a member, our club is a member of the Night Sky Network, which is in affiliation with the Astronomy Society of the Pacific, NASA, and JPL, Jet Propulsion Laboratory out of Caltech in Pasadena, California. And we get pins, or we can order pins for people who have been active in our club for whatever reason. It's called, you're a Night Sky Network star for.
I got one last time.
You're an astronomer?
Yeah. Yeah, I wonder sometimes why I need this hobby, I can't see. Anyway, okay, we're gonna make the awards. First
Read your
award.
own award.
First award, and I've got a certificate suitable for framing. This one goes to Sean Loescher, BBAA's illustrious president. Woo! And the second one is on the floor. The second one goes to Santiago, who has held all the BBAA executive offices.
First one of these.
Statesman. Shake my hand. Okay, good. Okay. Some of the people are not here.
So we're
So,
watching.
okay,
Yeah.
got one for Leanne Legault.
By the way, Paul and Doug Gross are watching live too.
Leanne is our esteemed newsletter editor. Got one for Bird Taylor,
All right.
our Mr. RRRT and Virginia Peninsula Astronomy Stargazers, D-Pass.
He's supposed to be here.
Got one for a young lady and her dad who have been very faithful for Boardwalk Astronomy and several Skywatch events, Chad and Caitlin Holm,
Oh, nice.
for supporting our BBAA. Got one for another VPass guy, Bob Berline, who comes out to Garden Stars almost every time we have it, and he's always at the Boardwalk when we're there too. This one, for supporting many BBAA events, goes to Michael Webster.
All right.
Thank you.
Griffin Green.
You're welcome.
And Paul Tardabini says hi to everyone too.
And this
People
one
message you.
goes to Rocket Man Abraham Jeff Goldstein, my twin brother.
Oh,
That's a long story about the twin thing.
There you go, sir.
Did you hear that?
Oh, I got something in my mouth.
oh.
That's the okay, thank you, sir. And and
Say
Jeff
that for
gets,
later.
Yeah.
no, since Jeff is up here,
Since I'm up here.
he is not only the Rocket Man, but the Sun Man.
No, the transit.
The Mercury Transit Award
All right.
from Woo! Astronomical League. We did all that work with the spreadsheet and the calculations and actually submitted
And
it.
there's a pin too.
There's a pin.
I didn't know there was going to be a pin.
Yeah, oh my goodness. I can't see what the pin looks like. There it is.
Take his glasses
Little
off.
sun.
It's got a picture of the sun with dots going across it. Mercury.
Thank you very much.
That's excellent.
Congratulations.
Thank you.
His big clap is for that spreadsheet.
Next one, he's not here, but he's been supporting many BBAA events. Jeff Thornton. Another one, our intrepid imager, who comes out almost every Saturday, Sunday, and Boardwalk Astronomy, Mel Spruill. He's also there at Skywalk almost every time. And the last one, I don't know who that is.
Jeff was interesting.
I wasn't going to, I'm going to give it to you.
Thank you, George, for coming to all the events that you do. George does the most part of
He
that.
does.
Thank you, sir. Thank you.
You gonna hold on to these then?
Yes.
Okay. Here's, Alrighty, next up is the secretary report, and Kayla texted me before the meeting. She said she'll have the minutes sent to me and I'll upload them onto the website, probably tonight or tomorrow morning. Okay?
Can you go over what happened last month from memory?
Do you wanna go over the new business section, is that what you're saying, or do you wanna go over everything?
I'm just kidding.
Do you wanna make a motion
I make a motion that Sean doesn't try to remember.
from memory?
Remember.
Oh, before I was gonna mention this, on these events, these are Eastern Standard Time. These are daylight saving time. So remember on the 8th of March, turn your clocks ahead.
Spring
Bring forward
Mm-hmm.
1 hour.
All right. Next up is the treasurer report. Chuck,
What?
do your magic.
All right. First, the bad news. We purged like 37 members on the 1st of February. However, we still have 120 members on the roster, which is 20 more than we had last year after the purge. So that's a good thing. There's about 6 people that are still, I didn't drop them because I knew that they were gonna pay probably, like Kayla and a couple other little ones like, there's 3 guys that will be due during the course of the year, because they joined in the middle of the year. But 98 people are paid, fully paid, and in good standing. And we have 5 honorary members, and we have a whole lot of associate members, but most of them pay the AL dues, so that won't throw off our calculation for the AL dues. If we have too many associate members that don't pay AL dues, the math could work out that instead of paying $5 a person for AL dues, we have to pay $7.95. So far, we haven't had to do that, but I just keep my fingers crossed. Overall, we're looking very good. In the general fund, we have $6,189.58. In the primary scholarship, we have $1,189.52. And the Georgia June scholarship's got $1,354 in it, for a total of $8,733.10. Kent sent me an email. I think he probably copied the rest of the officers as well, but he received a donation for, I believe, $250 for the Georgia June scholarship from Georgie's sister, or better statement, Georgie's family.
Yes.
So he's gonna send them a card of thank you for it, and he's supposed to be sending me the check. He's supposed to tell me either come get the check at his house or send it to me. So
He's
we'll
in
do
New
that.
York, so.
Yeah, he's
He
out.
probably doesn't see her, you know.
He's like, yeah, Chuck.
Just sitting around.
He's just blowing off. So anyway, things that we have to pay money for upcoming. We gotta pay our astronomical league dues. Other than scholarships, is our biggest draw. $660 a year to pay that. Our next biggest is insurance. We gotta pay insurance for in case somebody gets hurt. The new thing this year, the city of Chesapeake's making us, we had to add them to the insurance policy as an added insurer. Let me tell you, that was a pain in the rear. And it's done now, and we needed to have that for the Cornland thing, because the Cornland thing is something that we request from the city. We have permission to come out and observe, right? The Skywatch and Sunday on Saturdays is an event that they invite us to. So there's all kinds of little weird rules about whether or not they invite us or we're requesting whether or not we have to supply stuff. So, and the only thing we don't have anything in paper on yet is the city of Chesapeake set up an honorarium agreement with us last year so that we could get paid a little bit for every successful event that we did. Last year we had enough events that almost covered our fee for the Elizabeth River State Park, or Elizabeth River picnic location, right? I think we only had to pay $75 or $85 out of our pocket for it, right?
We had a bunch of cancellations last year, hopefully we don't have it this year.
Yeah, hopefully we won't, but we're not doing good luck yet. We already had to cancel January's. So, and February's in. No, we did not. February's in. 15. So, I agree, I hope that we don't have too many cancellations, but we still don't have the, honorarium agreement, and I've been sending emails to our Chesapeake brethren to remind them of it. But, you know, we were doing that for free for 20 years or more, all right? So it's no really skin off our nose if they don't give us.
We're still doing it.
We're still gonna do it, cause we've been out doing Saturday or Sunday on Saturday already without the agreement, so I don't think there's any big rush on their end to do it. So that's really about all I have. Our checkbook balance is fine with all the ways that I do it, between the statement and through the spreadsheets and such. Sometime in the next few months, we need to snag a volunteer to audit things, because we kind of got out of the habit of that happening every month or every year, and that's one of our rules.
Who did it last? Was it then you? And
Yeah.
it was, how many months ago was that, Jeff?
I think it was,
Wasn't that long,
December or something. I
It
don't
was
know.
sometime last year.
It
November.
was at the end of last year, I think.
Yeah.
When it happened.
Yeah, so sometime this
So
year.
just sometime in the whole calendar year it's gonna
Yes,
happen?
at some time we gotta do it. I think the audit before that was when I audited Bruce about 3 years ago. So, it happens and sometimes it doesn't, so. If anybody wants to know, our bank is BB&T. And, that's all I
If
have.
that's a debit card or a credit card, let me know and you'll be an officer if you get one.
Too bad it's not BBAA.
Well, we could have Bank of Geogga Data Systems. Let's see, that's about all I had, really. Does anybody have any questions about our funds or scholarship funds? I'm
Is the sheet
thinking,
even accurate, cause it says 2019 on it, so.
where does it say 2019 on it?
All over it. Predicted 2019 dues,
Mm-hmm.
2019 estimated.
I predicted this in 2019, yeah.
Time traveler.
That is necessary, right?
Yeah.
You see the top of this says.
The top says, says 2020. Nope.
Well, it looks like we're in good shape though.
I'm thinking that we might wanna augment our general fund. One of the suggestions that I was gonna talk to Ben Loyola about, if he was here, but he's too busy campaigning, is augment the scholarship funds with enough money so that both of them could be set at $1,500 a piece, right? It seems like we're making enough money that we could probably sustain two $1,500 a month or a year scholarship funds.
Make that a motion.
Do you
I don't
need
wanna
to-
do it without him here and talking to him about it. Cause
As you look back over
he
the
actually,
last few
according to
years-
the scholarship bylaws, he can alter the funds, the amounts, without, he can just take it up with the scholarship committee and do it. That's another thing, if anybody wants to be part of the scholarship committee, which means, when he sends out requests, or sends out the information to all the schools sometime, I don't know, spring, to all the schools in the area, and then we receive the packets in they're supposed to be in by the 1st of May or something like that. And they get together and then they look at all the packets to make sure that who's deserving and who's not. Last year we had a little bit of a snafu. We got one of the packets in a week after the deadline. It was marked, the postmark was marked before, but the packet was all dirty and crumbled, like it had been shoved somewhere. So my guess is our friends at the Lynn Haven Post Office dropped it somewhere and then found it and put it in our box. So we kinda had a screw up and we had to, by the time we found it, Ben had already awarded the scholarships and called the scholarship winners, right, and told them that they got blah, blah, blah. And, so we basically kinda had to award two last year, so. But,
Have you looked through the financials for the last few years to see if we're constantly having?
We are constantly growing up,
Okay,
getting,
so we probably could afford to get more.
yeah, that's why I suggested it, and, I think we can do that. One of the other things that I wanted to bring up, I don't know if it's new business or what, the Georgie June Scholarship Fund, we usually raffle something off. We've kind of been flipping and flopping about what we're gonna give off. The last 2 or 3 years, we've given a telescope, and a camera. Kayla made the recommendation at the last meeting, I think it was, to do one of those globes, like a Jupiter globe. Mobile globe. I tell you what, I have one of those Jupiter globes, and I love that damn thing. I can just sit there and watch it, because it moves all by itself. It just needs, it needs real life. Fluorescent lights don't drive it too well, but incandescent and sunlight, and it rotates all by itself. But that's a possibility. It's a couple $100. And what Sean and I were talking about a few minutes ago was something that every astronomer in here could use would be a good quality eyepiece, or maybe two, like maybe a high power and a low power eyepiece on the either, you know, maybe the Explorer Scientific wide view, you know, maybe the nitrogen purged ones, or the Nagler, maybe not Nagler, but the Teleview. Teleview has a new product line. I can't remember what they call it. The last one was like Ethos. This one is something else. And they have a lot of eye relief. You know what I mean? Like, so people, those old guys that have to have glasses, we can see come to focus easier. The longer the eye relief, the better it is for you with glasses. And they have a whole line out. And I was, you know, maybe a couple eyepieces we could give out of it, like a little set or something, you know, instead of a telescope. Because pretty much everybody has a telescope, and the telescopes that we gave away were pretty much entry-level types, right? And a lot of us bought tickets just to support the club, and but I think an eyepiece is a good idea. And I guess we were thinking about doing an informal poll of what people's favorite eyepieces are, maybe. And I'll
put it up on.
I'm gonna try and
Google
put a
website.
on our
Poll,
groups
yeah.
IO thing.
Yeah, Google I/O. Groups
Yeah.
I/O.
Is that what it is? What did I say?
I said Google
Do
I/O.
a Facebook poll too.
Facebook
Yeah, like
poll,
you
it's
said,
easy.
everybody thinks, I don't want to win a 6-inch doll. I would buy tickets and hope not to win, but an eyepiece.
Yeah, well,
sure,
that's, I mean, that's, well, actually, I was hoping to win last time, because I can give my grandson the scope. I didn't win it. And the other dingbat thing that happened was I had an 8-inch telescope that was Bernie's that I was trying to sell, right? I ended up selling that for $400, right? For that estate. I should have kept that, right? I ended up buying my grandson a Zoomo 8-inch telescope, right? It cost me $600 freaking dollars, right? So I should have kept that one. But I found this company that does this stuff it's called Easy Push To. It's like Orion's Go-To, but much more rudimentary. It gets you in the ballpark or something. But it's pretty slick. It only costs like $90, and it was real easy to install. So anyway, we're gonna try and do a poll of what the favorite eyepiece is. And if I can't do a poll, well then me and my mail merge function will be sending an email out to everybody. What's your favorite eyepiece? You know, because we want to try to get it going. We want to try to get them
I
bought.
think I sold that option on that website, right?
I think it's there. It's just
Yeah, can do it, yeah.
That's probably the best place to do it, because it's
Right.
hard. Even right now, what are you gonna do, have people list? What size eyepiece do you like, Joe? All
Inch
in
and a
favor?
quarter, 1 1/4, yeah.
well. I mean,
Yeah.
I was
I
just
believe
Well,
it's a 40 millimeter.
That's the one thing that you already down to, it's probably
Yeah.
gonna be 1 1/4 so everyone can use it.
Yeah.
yeah, pretty much.
But other than that,
I don't think we'll have any .965 ones, George. He's not interested. So anyway, that's all I got. See you, bye.
alright, well, you kinda covered the next section for the scholarship report, since Ben's not here. But since Ben's not here, did anyone here help him last year on the committee?
Yeah. Yeah, on the
And-
committee, I think it's him and me right now.
Is it?
I was gonna say, and if this campaigning leads into the spring, are you comfortable with possibly filling in for him? I'm just trying to lay groundwork right now, because we need you to like cover it. And
We're
then we'll
trying
get
to
volunteers to
suck
help.
you into being the chair.
At least for maybe this year.
Well, his office is convenient to my work office.
Oh, yeah, that's right. You
It's
work at
not-
Work Lending.
We usually get together somehow when we do it, so.
So we do got someone as backup, just in case. No Alcor here tonight, but we already handed out some awards. No triple RT report, anyone got anything? Does anyone know anything about it?
I
Has anyone used it in a while?
I haven't used it in a year.
I haven't used it in a while either. Okay, old business. One thing I had from last month is Chuck took care of our corporate information at the state corporate committee and renewed the post office box.
Well, I didn't do the corporate stuff. I did the e-postcard and the post
Oh, you
office
did?
box.
What are we about to do with all?
What with the corporate one?
Yeah. The corporate
Usually they send me a letter,
Okay.
and that's usually this month, usually toward the end of this month.
Where's the 990 thing?
Oh, every year we have to, we have to submit, since we're a nonprofit, that's our income tax fund. Since we don't have gross receipts greater than $50,000. If we did, I'd be in Mexico. But anyway.
You just have to file.
You got that on tape?
We have to file our e-postcard with the IRS every year stating that our gross receipts are less than $50,000, we're still in existence, all this stuff. And it's usually a pretty easy thing, and if you know what it is, there's a website right into the IRS to go do it, right? Now there's this little company called 990EZ or something like that, that somehow, I bet you IRS sold their list of all the people that are.
No, it's on the IRS website. You can look up any.
Oh, is it?
Yeah.
Because
They just copied the IRS's website.
You poke that, and now they want $35 to fill out your e-postcard and submit it, right?
All you do is check a box, right?
Well, you
You
have
put
to.
in like your tax ID number and say, I have less than 50,000.
Well, if they have you want to fill out this
I
form.
do this for other organizations.
Yeah.
It's
So
like-
it's really not
It's
that
a way
hard.
for them to make
And
money is all.
If
Yeah,
you
it
know,
takes 10 minutes.
if you've
Yeah.
done it before, you probably have IRS's actual website address of where the form is, right? So you can just bump right in there, and it takes 8 seconds almost. For me, it was like less than 30 seconds, man. Cause they remembered me from last year, or from the last times I'd done it. And all I had to do was just update the date, the year, and click the box that yes, we're under $50,000, done, right? But this easy 990, they want $35 to do that for you. And
They're not the only ones that do that sort of stuff. Go into the Virginia DMV.gov and see what you get. And you're gonna get about 45 companies that wanna sell you free stuff that you can get from wherever it is your state government you want. They'd be happy to sell it to you for $35. Just you ought to watch out for that.
it's a rack.
It is a racket. You keep wondering if they're gonna
That's
profit.
why I clicked and checked it on the asshole.
Yeah. Delete, and then that little section
That's the junk for
unsubscribe.
from now on, it knows it's junk, it just sends it away. Okay, that's all the old business, and I don't have new business. He raises his hand first.
Okay, he's first.
New business for the club. I've got a buddy that works at JPL, Jet Propulsion Laboratory, Pasadena, California. His name's Lee Torgerson. I already contacted him, and he's willing to do a presentation live via WebEx. I never heard of WebEx until I logged in, and now I'm a WebEx guy. They give you a free account if you want one. He's got an account, and you can go for more than 45 minutes. So he's willing to do it next month if we can. I checked with Sean. Sean said it's okay. I checked with George. He said it's okay. So does everybody?
Have a special camera.
Well, I was going to try.
Does he have to see us?
He didn't have to see that.
He doesn't have to, but it's a live thing with my phone, or I don't know if we can do it with this or my laptop, but we can do it via this. Maybe I can figure out how to plug it in so we can all see it.
Nice.
We'll figure it out. We'll
You
figure it
test
out.
while you're here,
Yeah,
like,
I'll test
They
it.
don't need the CO, we don't need a CAD on our end.
Yeah.
Yeah, you
Oh,
can
okay.
just go on there and,
Just implementation.
That's what
Yeah.
I'm saying.
yeah, it gives you the browser.
I do appreciate you laying that out.
Yeah.
Yeah.
Speaking of, we do have a presentation, I don't want to take too much longer.
Okay. And the other thing that I took the liberty of writing Joanna and Chip Gaines in Waco, Texas for the eclipse on 2024, and I got turned down. And not to take no for an answer, I wrote them again. Please reconsider, because the Back Bay Astronomy Club is very, very intensive outreach and those kind of people, and we're really intend on promoting their site, and we want to promote us and put us on the map, et cetera, and they still turn us down. So,
There's a lot of places in that path.
Yeah.
Over in that part of Texas.
Yeah.
Right? I'm gonna be pretty close to there by the time that happens. So maybe maybe BBA Northwest.
it's going right through Waco, Texas.
Right?
Wow.
That's gonna be a madhouse. It's gonna be, Waco is gonna be like, Cheyenne, New or, Wyoming was.
Right.
You know, there's gonna be so many people there. But there's also some other really good spots along that way. I've already been scoping out, took George's idea, churches, look for churches along that path and do that, so.
There'll be plenty of places you can go where they'll need an astronomer, especially if you have the telescope. That's what I learned from this last one.
Right.
What did you have though, Chuck?
Okay, real quick, since you said you get it. I sent out an email, probably everybody got it. We're gonna try and do another, apparel order. I've already got a couple orders for t-shirts. We have to have 25 of the wicking t-shirts. If anybody wants to see what one of them looks like, I have a couple here.
I'm wearing one.
Oh, is that one of the new ones?
No, it's a little slicker looking, but it's the same
Here, here, we can pass this one around. By the way, this one's for sale, this is a medium. And,
Who's a medium?
they're very
Get that
good,
around.
they're very light.
They're
My
great for the
grandson
sun.
could fit
They
in
are.
this.
Well, we've got all the way, I've got a large. I ordered the 3X and it fit okay. Usually I wear 2X, but 3X was comfortable because it was loose enough that it wicked everything very well. And he can attest to it. Most anybody who's done boardwalk astronomy in the middle of the summer can attest, and Saturday on Sunday can attest how well they keep
Yeah,
it
that,
cool.
this shirt is much better than this one. This was like that in the beginning, but now it's just cotton. So it just absorbs the moisture, and that one really still wicks the whole time, so.
And these are screen printed, so they're not embroidered. And so we have to have a minimum order of 25 shirts. They can be mixed of any size, color, whatever, but we have to have a total of 25 to order them.
And we're going to order extra. So if we have like 10, 15 people who want a t-shirt, we're just gonna order the difference so we can sell the rest throughout the year. Cause we always have somebody who wants a t-shirt.
And, all the rest of the stuff is embroidered, like, hats. I've got a coat back here. This is the current version of their coat. And, I have two other coats. Jeff Thornton ordered one of these last spring. And, when I got it and started fiddling with it, I said, man, I want one of those coats. 'Cause it's lightweight, but it's warm. It has a hood built into the collar. And here, you can pass this around to you. I washed it recently. But it feels lightweight, but it's very warm. I've worn this coat all winter long, back and forth to work. Yeah, be my guest.
Not good for
And
Montana.
there's George's hat, you get a hat there too. And what I was gonna say about the embroidered things are, we don't have to have a minimum quantity to order the embroidered items, which are the shirts, the golf shirts, hats, coats, things like that. We can order them onesie twosie. Okay, and the other thing is, once we do the order this time, I'm gonna try and make delivery for the two, I'm gonna try to have the order in on the 5th of March, the day after our March meeting. And then, I'll try to make delivery in April and May. After that, if you haven't picked up your stuff, you're either gonna donate it to the BBAA or we're gonna make arrangements to mail it to you. I found that I can shove 2 of these shirts in a $9 flat rate postage box, so.
But we don't wanna get into.
I do not wanna get into the mail order business.
That's why it's not available on the website. Moving on then, real quick, last thing we got is, droving report. Anybody got anything?
Jupiter's back!
It
It's
is.
5 o'clock in the morning.
Oh my gosh.
Good for you.
He is an early bird, isn't he?
Comment.
Yes.
I was with George at a Ocean Lakes Elementary School. 8 kids sitting there, and George just launched into, this is what we do. And then he mentioned the moon and Venus in conjunction. And I stopped and said, do any of you guys know what conjunction really is? And one little girl gave us the English language definition of conjunction regarding, amount of words, comma, this, that. And another little guy sat here and said, it's when like 2 things are real close together. And it was just like total absorption. How many moons does Mars have? 0. Mercury. How many does Venus? 0. They learned that in the 4th grade.
The only thing they didn't know is how many moons Pluto had. So
Yeah.
it's got 5 moons.
But it was really encouraging, if nothing else. Encouraging beyond words.
Very cool.
Thank you.
Very good, Arch. Good.
All right. There's no more observer reports.
Alright, let's roll.
Do you need me to introduce you? You good? This is
I'm
Rich.
good, I can introduce myself. I think most people have recognized me by now. If you don't, my name is Rich Roberts, BBAA member, variable star junkie. I do a lot of reporting for the AABSO, and I'm currently serving as their long period variable section leader. So I write stuff, like long period variables are kind of my jam. We'll get into that a little bit. But John's asked me to do a couple presentations where we've done some just like basic astronomy, basic astrophysics type stuff. And so we picked stellar evolution to go over the stellar life cycle today. It's kind of a fun topic, one that I enjoy. Because, way back in the day, Aristotle made the comment that the stars are inviolate due to change. And that kind of drove a lot of Western science for a long time. We didn't look for the variability. Actually, star variability was really discovered by many other ancient cultures, not Western science. But stars are definitely not inviolate. They change, they live lives, interesting lives. A lot like people do. They have kind of chaotic childhoods. They settle into a kind of a boring, workaday adult life. And then things start picking up and get a little hectic form as they age, and they start swelling in the middle, and they eventually die. And just like organic creatures, when we die, we go back into the ground, we kind of replenish the soil with nutrients and all that kind of good stuff, so the next generation can come back around. Stars forge heavy elements, all the stuff that you need for life in their cores, and then they disperse it back into the interstellar medium, so the next generation can come back around. And that whole circle of life begins again. But before I start talking about the life cycles of stars, I'm going to start with what makes a star, what makes a star go. For a long, long time, this question was not asked. Even back to the ancient Greeks, they were able to figure out the size, mass, of the sun, and realize that this thing was humongous. And so scientists just thought, this is some kind of special form of matter. It's crazy sun stuff. And so we'll not really worry about what it is. Well, then, as we talked about last month, when we started looking at spectroscopy, able to identify what the sun was actually made of in the mid-19th century, and said, it's just hydrogen, there's carbon, oxygen, just normal stuff that we see every day. Then we had to change the game, because they're like, it's not crazy sun stuff, it's actual things that we know about. And so what kind of process can produce that kind of energy output? You look at something like combustion, chemical processes, easily dismissed because the sun would burn up under those processes in a few thousand years. Obviously, we've been around for a few thousand, longer than that. Had to be wrong. 2 pretty smart physicists, Lord Kelvin, who the temperature scale is named after, and Hermann von Helmholtz, started exploring the idea of gravitational contraction. They realized, this is a huge ball of gas that's going to be intense gravity there that's going to try to compress all that gas towards the center. As it compresses, it's going to get hotter. When temperature goes up, as we talked about last time we did the black body radiation curve, you start getting higher energy photons. It can incandesce in the, it can condense in visible light part of the spectrum. So they said, well, does this match, that's what you do in science. You take a model, or you take what you observe and you try to model it. They're able to check all the boxes. They're like, we can get the energy output we need. We can get the temperatures that we need. Does it last a long time? Well, they came up with a few million years. They checked the box. They didn't bother anybody because we had no idea how long the Earth had been around or the Sun had been around. So a million years, you easily buy that. Humans certainly haven't been around for a million years. Our society's been, the written language has only been around for 5,000 years. A million years seems like a really long time. Well, in the early 20th century, the geologists came and rained on our parade. We thought we had this good model, but when they started studying radioactivity and they developed the ability to radio date things, they said, dude, we got 4 billion-year-old rocks here on the Earth. Check yourself. Because obviously that million-year-old sun model doesn't work anymore. We needed some other kind of process that could last long enough for the sun to exist. And we know that process was hydrogen fusion. They didn't realize that until the 30s. But keep some of that in mind. So now that we talked about, hey, what makes a star, how does it get to that point where a star can fuse hydrogen? It all begins in giant molecular clouds. Here's some famous ones. These are some of Hubble's famous images with the Eagle Nebula, the Horsehead Nebula, the Pillars of Creation. When I say giant, I do mean giant. These clouds can span tens to hundreds of parsecs. The giant molecular cloud where a lot of the star formation is happening in our galaxy right now stretches across the constellations of Orion, Auriga, Taurus, Gemini. It's monstrous, right? In that cloud, it's going to develop dense cores, and that's where stars form. Stars kind of form in bunches. And whenever you see an open cluster is a bunch of stars that just recently been born. They were born together. At one point, our star was born with a bunch of other stars, and we've since been dispersed across the galaxy because we've gone around the galaxy 20 or so times since we were born. So how that process gets kicked up is these big, dense clouds of hydrogen. It's kind of impressive. If you just go to Google Images, another word for them are dark nebula. Just like Google Image dark nebula, you'll see these rich star fields, and there's a big hole in the middle of the star field. It's not that there aren't any stars there, there's no hole. It's just the molecular cloud is blocking all the background stars because these are opaque to visible light. This is kind of the next generation where we're really starting to study the interiors of these things, but you have to do it in near IR wavelengths. So if we could ever get James Webb up there, because you can't do near IR very well.
Without a near IR.
Yeah, you got to get up in space to get away from all the heat and stuff of interference of the Earth. So something has to keep these up. So left to their own devices, it'll sit there, but something will stir it up. Maybe a supernova explosion can blow up and kind of bring ripples through these clouds. You could get a dwarf galaxy across the plane of the Milky Way, and that stirs up a lot of gas. That's probably what happened about 5 billion years ago when our star was born. That was the last baby boom. We're a baby boom star of the galaxy. Stars were being born in the galaxy back then at about 10 times the rate that they are now. But it kicks up the dust, it starts collapsing together. You get these dense cores, and inside those dense cores, there's other pockets of density where stars happen because gravity, you get the ball of gas, gets a little gravity, so it attracts more gas, gets more gravity, which attracts more gas, and it just starts snowballing until it gets so big. And as it starts growing, guess what happens? Well, as it gets enough gravity, that gas is going to start to compress. It's going to start heating up. It goes under Kelvin-Helmholtz contraction. So it's a real thing, but it's not what makes stars go, it's how stars are born. When you start getting that Kelvin-Helmholtz contraction, you have what's known as a T-Tauri star. T-Tauri stars are not actually stars. They're called T-Tauri stars and have a traditional variable star designation, T being the third variable star found in Taurus. That's a whole other one if I talk about how variables are named. But if you look at this, it looks like a normal star, right? It got so hot from this Kelvin-Helmholtz reaction, or contraction, that it's hot enough that it incandesces in the visible light parts of the spectrum. So it looks like a star. but there's no fusion yet in the core. So what's happening, that gas is collapsing down, pressure, temperature in the core is rising. But it's kind of like at this point, it's kind of like an arm wrestling match, where gravity is Arnold, I am temperature, and I'm trying to arm wrestle Arnold. He easily overpowers me, right? I had no resistance. As it gets hotter, you give a little bit more resistance, but no real challenge for Arnold. You know, it's like if I started juicing, I'm still not going to be able to beat Arnold in an arm wrestling match. Well, at some point, temperature gets high enough that the game changes, and that is, it gets hot enough that hydrogen fusion starts to begin. And then you get in this gridlock where those fusion reactions create photons, which cause a radiation pressure that puts out. It counterbalances the force of gravity pushing in. So now it's like your arm wrestling match is Arnold versus Arnold. They're equally strong, and they hold each other in this equilibrium that can last for, you know, billions of years. And T-taris are variable, mainly not because of any physical thing. It's mainly because they're all surrounded by disk, you know, dust disk, which are protoplanetary. That's where your planets form, part of the star. So it's just as that dust gets in the way, they rapidly vary. So, hydrogen reactions. When fusion begins, I won't harp on this too much. There's two main reactions that happen in stars. Low mass stars, when I say low mass, I mean 8 solar masses and below, go under what's known as the proton-proton chain. Bigger stars do this. This is the carbon-nitrogen cycle. And you know, if you look at how many stars are 8 solar masses and below, that's probably like 98% of stars. Very few stars get this big to go under this. But in the beginning, you have a couple. You get a couple protons. They go to a series of reactions. In the end, you get an alpha particle or a helium nucleus. They called them alpha particles. They didn't know what they were. They named them stuff before they knew what it was. It's a common theme in science. One thing to take away from this, because it'll play in, these series of reactions have different probabilities to occur. This first link in the chain where your two hydrogen nucleuses come together to form this deuteron takes on average 1 billion years to occur. So it's highly improbable. But there is so much stuff in the center of that core of the star that this happens trillions of times per second. So it's kind of like, yeah, it's winning the lottery is pretty improbable. May say it's 1 million to 1, but if I have several trillion lotto tickets, I'm going to hit the lottery, and I'm going to hit it often. But that does come to play a little bit later on. So now we're burning hydrogen, doing fusion. Here's the HR diagram. This is the third time I've talked to this group. This is the third time I've put this diagram up. You don't get away from stellar physics without looking at this. So I won't harp on too much, but on your y-axis, you can, it's interchangeable. You can do luminosity, brightness, energy flux, you name it. On the back, you can do spectral classes like we talked about last month, or temperature. So over here in this side, these are your hot stars, these are your cool stars, these are your dim stars, those are your bright stars. When you start fusing hydrogen, you're on what's called the main sequence, and we talked about that before. But this is where adult stars reside. 90% of the stars are on that main sequence of this chart. So they're kind of boring at this point. They're just going around burning hydrogen. They'll do that for billions of years. One thing to take away, these bright, hot stars that are up here on the main sequence, those are your really massive stars. Mass drops as you go down here. One thing you would think intuitively is this big star, it has way more stuff, so it should be able to last longer than these little guys down here that are 10% the size of our sun. But actually the opposite is true. Those massive stars burn fuel so efficiently that they'll only stay on the main sequence a few million years. These guys down here that are 10% the size of our sun will stay on them and they can be there for 1 trillion years. Our sun will stay in this state for a good 10 billion years or so.
So does that mean it's a pretty good chance that the small stars may have been initial stars that was forming the galaxy?
When you look at, that's one of the ways that we date things, is look at the age of the stars. Like when you look at globular clusters, you will see no star in that globular cluster more massive than our sun. The G stars, there's no O stars, B stars, A stars, nothing in those globe clusters. So those are all about 13 billion years old. They formed at the same time our Milky Way formed. So all the heavy stars have already evolved, and they're gone, and it sort of becomes very red. If you look at things like the Orion Nebula, last time I talked about how the Orion Nebula is lit up and how the O stars are doing all that. Well, as soon as those O stars are the first to go, the Orion Nebula goes away. So a lot of the other clusters, you'll see there's very few O stars around. You start looking like Pleiades, some of the clusters in Cassiopeia, they have A and B stars. All the O stars have already gone. So they're a little older than the stars of the trapezium. So that is one way they think. The other way we can tell if a star is an original star or not, I'm getting off topic here, but that's okay, is metal content. Original stars that are first generation are only going to have hydrogen. They're not going to have things like carbon and oxygen and stuff in their spectrum. They're going to be deficient of all those. Because when they first formed, or the galaxy was early on, that's all there was. Is we'll talk about those original stars made a bunch of heavier elements, blew up, dispersed the galaxies, and the second generation, third generation stars came about, and they had all those metals in it. Like our star is a second generation, potentially a third. There's no real way to tell other than, but because we have metal contents, we had all the stuff that made the Earth, we know that it was not a first generation. Yes, sir.
I just want to digress a minute. When you have your gas cloud and it starts to condense, how does a disk form for the protoplanetary thing? Because you have to have momentum. And if it's a big, if you don't have some kind of vorticity in that cloud, you're not going to get that, at least in my opinion.
Yeah, it's pretty common. If you look at physics, anything that's rotating, you have to have some kind of rotation, right? And to conserve angular momentum, things just flatten down into a disk. Nothing goes straight in. If you look at like black holes or streamers on anything that's come from a rotating core, to conserve momentum, they can't go straight in. They end up spinning around. Because gravity is also warping the space around the mass.
And what starts the spinning?
Can gravity start the rotation?
So as things collapse, nothing's coming straight in, but you start warping the space more and more and more. Stuff coming in, falling is going to follow that curvature in space-time, which is going to give it a little bit more of a circular, than it flattens down to a disk.
Yeah, but that curvature is a sphere all the way around, right?
Again?
The curvature of space around the central of gravity.
It's actually
is a
four-dimensional. You're starting getting a
No,
little
I understand.
past my ability to comprehend
Oh, okay.
stuff,
Oh, Lord.
but it's not. You have to start thinking in multi-dimensions there, and I'm not very good at it.
No, he can only do this.
I can only do this.
You're doing a great job.
Yeah.
Thank you very much.
Yeah, but
Some questions.
maybe as a follow-up, because I do know that hey, because of angular momentum conservation, you are going to start spinning it and flatten out into a disk. Well, I probably can't adequately explain all the dynamics going through there.
Well, any cloud that's floating in the galaxy is going to have some slight amount of rotation to it. And as the thing collapses, and it's going to collapse by magnitude in size, that rotation, a little bit of rotation it started with, is going to be amplified, because conservation of angular momentum is always conserved, because that is a law.
As it gets smaller, it gets faster, just like a.
Yeah, it's the ice skater
Like the ice
example.
skater.
When you hail out here, you go slow, and as you pull in, you're exactly right. As that cloud goes down, it goes down.
Not to say.
All right, so getting back to the HR diagram, we talked about the main sequence, but we'll start to see, this is one thing that threw them off. Like they noticed when they started developing this graph, almost all the stars were on the main sequence, but we had these other populations up here. These, they call red giants, red supergiants, because they're like, these have to be really big and they're very cool. They didn't really know why, but there's populations of stars off the main sequence. And across the yellow spectrum, the yellow giants, there's this instability strip. We'll talk a little bit about that too. So now we'll start migrating into why are stars in these other parts of the HR diagram and how they get there. So to do that, we'll talk about what's going to happen to our sun. This is a single solar mass star is just doing his thing, his workaday life on the main sequence. This is just, like I said, it's adult life. You go to work, come home, eat dinner, watch Jeopardy, kiss your wife, go to bed. Do it, rinse and repeat for most of your life. Then all of a sudden, well, not all of a sudden, no, gradually over time, is when you do that proton-proton chain, where we started with a bunch of hydrogen, now we're making a bunch of helium. All that helium is going to be concentrated in the core. And also those hydrogen reactions are very improbable. So as you start building up more and more helium in the center, now you're kind of contaminating your fuel, right? So the hydrogen fusion reactions actually start moving out from the center, and you start building up an inert helium core. A couple things physically to the star begin to happen as that occurs. It starts to get brighter, and the envelope starts to expand out. So as the envelope expands out, the surface temperature starts to cool, so the star becomes much, much redder. And in the HR diagram, it starts moving up into the right, into that giant region that we saw before. The internals of the star starts looking like this. You have this hydrogen burning shell. You have this inert helium core. If you look, hey, we know this is what the solar system looks like now, but by the time we evolve into this red giant state, our sun is going to expand out probably close to the orbit of the Earth. Some people think we'll may surpass it, but it'll be pretty close either way, and the Earth will no longer be a very good place to live. Habitable zone starts pushing out toward Jupiter and Saturn.
Will that throw the planets around by the sun enlarging, changing it?
See, not necessarily.
Gravity changes, variable gravity?
Gravity's not really going to change, because if you look at Newton's laws, like gravity only cares about the center of mass. So really all the gravity functionally is from the center. So all these planets care about in its orbit is the mass that's inside the orbit. So that really is not changing. Right? There will be some tidal effects, obviously, when, so now that envelope is more famous, you probably get tidal effects on the Earth, which could throw it off. But for the most part, gravity is still functionally going to be the same. That's why people are like, what if we made a black hole where the sun is? Well, if the black hole is the same mass as the sun, the orbits of the planets aren't going to change. As long as that mass inside the orbit is the same, the orbit's not going to change.
Just be a little cold.
What's that?
It's just be a little cold.
Yeah.
It'd be pretty. So that's what's happening here. Now, eventually, the whole time, gravity is still acting on that hydrogen, that inert hydrogen core, and squeezing it down. As it squeezes down, it gets hotter. Hydrogen fusion happens at about 10 million degrees. We got Kelvin-Helmholtz contraction again happening to the core of that star. When it gets about 27 million degrees, helium fusion can begin, and you get something new happening. You get that helium that's built up in the core follows a series of reactions, and you get carbon and you get oxygen. So when this happens, the star moves on to what's known as the horizontal branch. It's very exaggerated in this diagram, but the star starts heating up again a little bit. And so now you have hydrogen burning shell, helium burning core. But that helium burning core is starting to produce a lot of carbon and oxygen, which is like we did with helium. Starts building up in the core, and you get to a point where that stuff is inert, and you move on to the next leg, which is called the azimuthine giant branch. This is my jam here, because this is the land of the long period variables. And AGV stars are very interesting. A lot of cool stuff happens. So you have this inert carbon oxygen core. You have a helium burning shell and a hydrogen burning shell out there, and an extended hydrogen envelope. These stars are not entirely stable, so they pulsate. And that's what it's one of the main causes of their brightening and their dimming. Pretty substantial. I mean, they can be several orders of magnitude. There's also things like titanium oxide in the envelopes that'll condense and evaporate in these pulsation cycles that drive it even further. But that helium burning shell also lays dormant at times, actually a lot of the time. And then as the hydrogen fusion makes more helium, it'll have a thermal pulse. The helium will flash, go under a thermal pulse, and it'll lay dormant again, and it happens over and over again, usually 10 to 20 times or so on the sun. When those thermal pulses happen, you can also get what they call dredge-up events, where the carbon from the core gets filtered up to the envelope. As you start building up carbon in your envelope, you get a nice, beautiful carbon star. So these guys, they also, the envelope extends even further. So by the time our sun is in the AGB stage, the envelope could be reaching out as far as the Kuiper belt. These stars also develop pretty strong solar winds. So by the time they get more evolved in the AGB branch to the carbon star state, most of them have like detached circumstellar envelopes and stuff like that. So that makes them even dimmer because you have all that dust out there that obscures a lot of visible light. But these are intense infrared radiators. So these are fun stars. These are what, these are your Myra stars. These are my regular variables. And this is what I mainly concentrate on. So eventually, like I said, these have strong solar winds. They have detached shells. Well, eventually those fusion reactions, just before they can't sustain themselves anymore, they filter out. And that envelope just filters, turns off into space, and you have a beautiful planetary nebula. The planetary nebula eventually will just dissipate over 10, 20,000 years or so. But and you're left in the middle of that planetary nebula is the inert carbon-oxygen core, because the mass is never sufficient for gravity can track that down for it to get hot enough to where carbon and oxygen fusion can occur. Something else is keeping it intact, which we'll talk about later. So that's lower mass stars. That's what stars that are, less than 8 solar masses or so will do. Some stars that are more like in the 5, 6 level solar mass range, they can get hot enough to burn carbon and oxygen for a little bit. And so most white dwarf stars are carbon and oxygen. Some are the ones that are big enough to have carbon oxygen fusion for a little bit. They may have to be like magnesium and neon, things like that. If you look at the evolutionary track for bigger stars, like, okay, this is log on each side, so log luminosity, log on temperature. Evolve like this, kind of what we're showing. Now the more massive stars kind of shoot straight across the HR diagram. They don't go up and to the right, they shoot more across. So these are the ones that when they pass through that instability strip, when they're yellow giants. And those are your areas of those are also pulsating stars, but they pulsate very rapidly. Those are your Cepheid variables, your R Laurae stars, your RB Tau stars, which we talked about when I did the variable presentation like a year ago, the importance of those to distance measurements. That they also have pretty good extended back horizontal branches that they kick back when they go through different orders of fusion. Then the really big stars like Betelgeuse, for example, they have cross supergiant branch up here. But they're a little different, and they're so massive that they can drive higher and higher orders of fusion. So you kind of get the same thing again, where heavier elements are built in the core, that starts to fuse, that makes even heavier elements. One of the things that's interesting about this is each of these shells, you start getting this like onion effect. But as you get heavier and heavier elements, every time you have a fusion reaction, you get less and less energy out. And I'll show you why in a minute. But those layers exist for shorter and shorter periods of time because these are not very efficient reactions. And so, you get up here, maybe carbon oxygen may last for a couple hundred years. You start getting some of these neon magnesiums, those reactions may last for a couple months. We can tell something's about to go very, very wrong with silicon and sulfur fusion stars. That reaction will last for like 10 to 12 hours in these stars. That's it. But when those reactions start happening, the star starts flooding out an enormous amount of neutrinos. And we have big neutrino detectors which can detect those events. So like when Betelgeuse, everyone's like, hey, is Betelgeuse going to blow up? Probably not. But we'll be able to detect that and have about a 10 to 12 hour warning that it's about to occur. Because the next stage, you start building up nickel and iron. And nickel and iron is actually an endothermic reaction. So it can fuse, but it actually takes more energy goes in than comes out. So now that you have energy going in, not coming out, you have nothing to fight up against gravity. Once you have nothing pushing against gravity, that core collapses and you have a big old explosion. The star just blows up.
And I've read somewhere where it says that we have minutes. When that starts, it's probably less than an hour before it goes.
Yeah, so those last reactions, I mean, it's insane how fast. You think of something that exists for millions of years, and you get to these steps of evolution, you're like, oh, that only lasts for 2 weeks. This step is a couple days. Then you get down into the hours range.
And you're able to measure these things in this day and age. When a shell burns up or collapses in on itself, you see some sort of source of light that's letting you know that that's coming out.
Right. We do have early warnings, and it's the neutrinos. Neutrinos, we're bombarded with neutrinos every day. Our sun produces a ton of neutrinos. It was in the proton-proton chain. One of the first leg kicks out of neutrinos.
Okay.
But they're very hard. Those things are very non-reactive. There's millions of neutrinos going through all of us this second right now. So they're hard to detect. How they do it is they have these humongous, basically they're like vats of cleaning fluid. Like the biggest one is in Japan, Super K. It's a big freaking bowl. Has all this fluid in it that will react with neutrons. Like 1 per several trillion neutrinos will react. Yeah. And when it reacts with that chemical, it'll put out a photon, and it has all these detectors around. It's a pretty cool picture. Go Google Super K, and you'll like do Google images on it. It's impressive. The first time we saw this surge, I believe, I could be wrong on this, but I know before supernova 1987, there was a big hit. All the neutrino detectors across the world. There's just a couple of these. There's one in Italy. Everyone's like, what just happened? There's all these neutrinos. And then we saw that supernova go off hours later in the large Magellanic Cloud. So they started calibrating them to give us better warnings when these are about to happen, because you get this flood. It's enough to drive a lot of reactions.
Neat.
But when these supernova remnants, this is a picture of the Crab Nebula. I couldn't see this when I lived in Hampton, even my 11-inch SAT. I can now that I've moved to Carrollton. But as I said, these supernova are responsible pretty much for everything that we need for life. When they started examining, it wasn't this one, it was the remnant in Cassiopeia. It was the remnant of Tycho star that went off in 1572 or 74. They found hundreds of Earth masses worth of carbon, hundreds of Earth masses worth of oxygen and silicon, all the stuff, all the iron that you need for your blood, all the calcium for your bones. It was all forged in these really big stars that went through a core collapse and blew up and distributed all those elements back into the interstellar medium, so they could, pretty much salt one of those big giant clouds, and we could have this, the cycle begin again. But I mentioned, I was debating whether to throw this in or not. Nuclear binding curves, but one of the reasons why those reactions start happening faster, they get less efficient. What's happening in fusion reactions, it all goes back to Einstein and E equals mc squared, right? If you take a proton and a proton, add them together for helium, that helium weighs less than the aggregate mass of the two hydrogen atoms. So that change in mass is the energy that's released, because they're interchangeable. As you start going up and up, and this has to do with the strong nuclear force that binds nucleuses together, acts over some veins. As you start getting heavier, that force is stronger, you have less delta in mass as you go up. When you get to iron, it's like the sweet spot of the distance that the strong force can react over versus electrical repulsion. So that's a very tightly balanced, very stable nucleus. Supernova explosion is powerful enough to start driving some of these heavier elements that are created in those, but those are all radioactive because now the force can't act over the whole distance of the nucleus, and so eventually they split apart and they start fission. So one thing I didn't talk about, I'll talk about now, are remnants. Like I said, hey, at the end, when the stars exhaust its nuclear fuel, we'll go back to low mass stars, the planetary nebula occurs, it leaves this white dwarf there. Now, white dwarf is still very hot. It's not very luminous, but it's not creating its own energy anymore. That core at one point was like 20 million degrees. It's just radiating its leftover heat back into the interstellar medium, right? Just like if you have a pot on your stove, it's boiling, and you cut the gas off on your stove, the pot's still hot, and it takes time for it to cool back to equilibrium with the environment. It has to radiate its heat away. Well, that white dwarf has a lot of heat, and space is not a very good conductor. So it takes 1 trillion years or so for a white dwarf to radiate all its heat back away. So much so that no white dwarf ever created has radiated all its heat away and cooled off completely.
Okay.
But something's holding up. So before, like I said, it was the fusion reactions that were fighting up against gravity, right? And holding that star from collapsing down. We got the supergiant, it collapsed down. But in lower mass stars, that carbon-oxygen core is being held up what's called electron degeneracy pressure. This is kind of a weird concept, took me a while to get, but if you're here last time when I showed models of the atom and all the different energy levels that electrons can bounce up and down from, and that's what produces absorption lines and emission lines and all that kind of good stuff. Well, there's a concept or a law in quantum mechanics called the Pauli exclusion principle. It says no two indistinguishable particles can be in the same quantum state. So these have different states, these electrons have different states that they can be in. Gravity starts pushing all those down into the lowest energy states that are possible. And at some point, it can't push them down anymore. As soon as one guy's in this state, nobody else can be there. Then he's got to go to the next energy state, and they just stack up. And that produces a pressure. Kind of like if we were all in this, against a wall and someone started pushing up. There's a point where you can't push us anymore. So our bodies put pressure. That's what's happening here. Now, at some point, gravity can and will win. In the 1920s, a physicist Chandrasekhar calculated that at 1.44 solar masses, gravity is strong enough now to overcome that electron degeneracy pressure that's happening in the white dwarf. When that happens, all those electrons are pushed all the way down into the nucleus. When they get there, they meet up and combine with the protons there, and you have a bunch of neutrons. And so you have a neutron star. And it's neutron degeneracy pressure at this point, which keeps it battling against gravity. At some point, when you get to about 2 solar masses worth of neutron star, gravity wins again, and it collapses down to a black hole. To put some kind of thing on size here, if you took a white dwarf that was the mass of our sun, it would be the size of the Earth. So you think about that, our sun is something like 3,300 times bigger than the Earth, right? So you take all the mass of the sun. It's mind-boggling to think of the size of our sun, right? I talked about this last time. If you went straight line from the core of our sun to the Earth, 20% of your travel would be inside the sun itself. You're taking all of that mass, putting it inside of the Earth. That's how dense these things are. Now, if you go to a neutron star that was a single solar mass neutron star, it'd be about 12 miles across.
The sun?
The mass of the sun
Yeah.
is 12 miles. So if you think about it, I drive from Carrollton to Norfolk to go to work. I drive 2 neutron stars worth of commute every single day. Now, when I say 2,
What kind of mileage do you get?
I would not get very good mileage if I was trying to drive on a neutron star. Yeah, when they start talking about, hey, what would it be like on the surface of a neutron star, it gets kind of crazy. The amount of energies it takes just to move an object like a centimeter on a neutron star is pretty mind-blowing.
Wow.
But to get some of these sizes too, you remember the mass, this is all the mass that was confined in the core. So in order to get to a neutron star, you have to have at least 8 solar masses initially when it was on the main sequence, because it loses a lot of that mass. To get to a black hole, if you look at something like Betelgeuse, which its progenitor we think was in the 16 to 23 solar mass range when it was a main sequence star, it'll become a neutron star. You need about 40 solar masses initially to get up here. There's not many stars that big. There's like 20 to 30 or so in the entire galaxy that are big enough to actually get there at that stage.
20 to 30 stars in the Milky Way.
Yes.
Okay.
Only a small percentage will be big enough to ever reach neutron state. You know, maybe 1 or 2% are big enough to get into the neutron star stage. So a fraction of that are big enough to actually get to black hole state. So here is, I found this chart like several years ago. I can't remember where I saw it when I was just looking up stuff, and I kept it, and I was like, I finally have a chance to use it. It's been sitting on my computer for years. But, you know, it was a cool flow chart of everything that we just talked about. You start with a molecular cloud to open clusters, and then depending on the mass of the stars, you go down different avenues, from a massive star to a red giant to a supernova to a black hole, a neutron star. The lower mass stars get a right through. A lot of stuff is fun to happen. Most stars do end up in binary pairs. We're kind of an exception that we don't have another star with us. So these get kind of fun when you have a white dwarf paired with either a main sequence star or a red giant, because the white dwarf will start accreting mass off the lower mass star, or the secondary star. And then that's where you get things like all your cataclysmic variables, your dwarf novae, your type 1a supernova that happens there. And there's a bunch of different cool types of dwarf novae. I talk about them a little bit. If you go back in the newsletter, I think it was August, I wrote an article called "The Stars That Go Boom." It's all about these guys right here and all the different novae configurations. You get the planetary nebula and a white dwarf.
What are you getting to with the dashed lines?
These are, not every star goes that way.
Okay.
Yeah, so this is a kind of an offshoot depending on the dynamics of the system. So yeah, if you're in a binary pair, you're going to end up over here. This, I think they just took it out, because after you have the supernova, a remnant's left, you get the supernova remnant, and after time when that clears, those are what's left over at the center of that reaction. So that's all I got.
Very good, very good. Talk some more about Betelgeuse. I know it's about between 500 and 800 light years away, and we're getting light from Betelgeuse that's 500 and 800 light years old.
Yeah.
And so it's dimming. It's going down to 1.5 magnitude, about the same brightness as Bellatrix.
Yeah.
So what's with it? What's going to happen?
It's interesting you say that, because if you go to the Facebook page, I wrote an article about it. It's also now posted on the main page. If you go to the AAVSO website, on the sliders down there's a link to it. So I talked quite a bit about that star and what's going on. But just earlier today, I got an email from Dr. John Percy, who's the head of the physics department at the University of Toronto. He's also the guy that wrote the book on variable stars. I know because I have the book. And so, in addition, one of the things he was thinking about, I think there's a couple things that are possibly happening. So Betelgeuse has 2 periods, right? And it's very common for big stars that are in their pulsating modes. One of the periods is probably driven by pulsation. The other one is by convective sails. Betelgeuse rotates. It has a strong magnetic field because of that rotation, which causes massive convective shells, which are cooler. So it has hot spots and cool spots. That drives the secondary period. We're at the dim spot of both periods right now. So this occurs at times, and when those 2 things align and it hits both dim spots of both periods at the same time, it usually drops to about 1.0. We're at 1.5. But one thing that he's noticed when he was doing when he was looking at it, is over the last 10 cycles or so, the amplitudes of both those periods have been widening. So you're starting to get bigger spread, both top and bottom, on both periods, and they're both aligning at the same time. So he thinks, yeah, convection is a possibility, but it also is probably a fact that those amplitudes have gotten wider, and they're both hitting at the same time, which is probably why it's historically dim.
How long is it going to stay?
What's that?
How long is it going to stay like that?
Best guesses are another 100,000 years or so. So we got time before it blows up. It's going to blow up.
No, but I mean, when will it start brightening back up again?
Oh yeah. So they're expecting that we're hitting the low point now. It was supposed to like early February was predicted to be the lowest of the low points. And if you start looking at the photometry, we are starting to level out. It does appear to be bottoming out. It's no longer dropping anymore. It's kind of settled out. So we'll see. If it continues to dim or doesn't start rebrightening over the next month or so, then something else is going on. There is also the possibility too, if you look at Betelgeuse, like I talked about when you get to these evolved stars, it has a very strong solar wind. It has two actually contacted circumstellar envelopes. So there's a layer of gas and a separate layer of gas outside of it. And it's pretty cool. If you see it, it's traveling through space. It has a pretty high proper motion. So it kind of looks like a comet almost. If you look, there's a bow shock that's happening where it's hitting the interstellar medium, and it has this long diffuse tail where all this gas is kind of shrinking away. So if the gas is getting really thick, that stuff is typically opaque in the visible range. Because the other thing that's happening, we have not seen any dips in the IR parts of the spectrum. If Betelgeuse radiates most of its energy in the infrared, so its bolometric luminosity hasn't really dipped all that much.
So it's like a 4 or 5 month cycle that it's going through or something.
Yeah, it has two, like I said, 2 periods. The pulsation period is about 400 days. The secondary period happens every about 2,100 days, and they just happen to line up. And this happened before where we got dips, just nothing to this extreme. Yes, sir.
Has anybody calculated the flux of the Earth when the thing goes supernova?
I do not know how bright this is. I know it's been done, and I've seen it before, but it will be very bright. Like, I believe, don't quote me on this, that it should be bright enough to see in the day.
That's
Oh, wow.
Yeah. It should be daytime.
Yeah, the thing with supernovas too, they kind of have they
Course,
start
around
off and then
essential,
over a couple of
around
days they
Saturday.
brighten and then they start to dim down again. So we'll be able to see it
Oh.
very brightly for several months after it goes supernova. But at the peak, we should be able it will be bright enough to see
What
it
did
today.
you say?
I don't know, we get a lot of gamma.
Yeah, what?
A lot of gamma.
Nothing to be worried about. It's far enough away. I think now a supernova has to be, again, don't quote me on this number, but I believe it has to be within like 100 parsecs or so to be really dangerous. And Betelgeuse is 200 parsecs. It's not going to pose any kind of
500-600 light years.
Yeah.
It's a long way off.
yeah. Don't quote me on that one. And maybe 100 light years. There is a point where a supernova too close would be very bad.
There you are.
That's not in the radius where it would be really bad or enough where it would cause any kind of issues, I don't believe.
It's further away than you care to drive in the day.
That's right. Well, you couldn't because you can't move but a centimeter. Thank you, Rich.
Very good. Thank you. Good job.
All right, right on time. Anything else there before we adjourn?
Go
Did
Navy.
anybody pass around the sign-up sheet?
Nope.
Don't leave. You gotta take care of it real quick?
Yeah, as you leave today, write your name on
We
the
just
sign-up.
we can just say it on the tape here. Do it that way.
Well, this is for Kayla.
Yeah, this is for Kayla. We can say, Kayla, can listen to this.
I don't know if she wants it. She may not like that.
On March, the day after our March meeting.
I would probably fail.
Meeting adjourned. Thank you for coming.